Okay. Okay, so and you know that question 2 started from where we question 2BVI, sorry. Let's go up to see what we've got there. Okay, all right, so that's module 4 question 2. So it started by saying we should find the basis and dimension of a particular subspace. That's the A part. And then the B part now give us a particular matrix, so matrix A, and then asked us to do some stuff. So at the VI, it started asking us to show if a particular matrix U is in the column space. Let me find it. Okay, VI. Yeah. It says we should determine if U is in the column space of A. Okay, and then we said that to achieve that we need to show that that there is a vector X that you will multiply with matrix A, and you will get your U. Okay. So but then even before or using that approach, you can clearly see that your U cannot even be in the column space of A, because where is our U? This is the U we are given, and our U is let me be sure of where our U is. You know, this is a continuation, so we need to be sure of where we stopped. Okay, so U has 4 entries. That's this: 3 minus 2 minus 1 and 0. while the column space of A is in R3. And where is the column space of A? Remember that the column space of A is what we got after we reduced A, we did a row reduction on A. And if you do the row reduction on A, this was where we did it, and we saw that the dimension is 3. Okay, and of course, how did we get that? You could see that after the reduction, the column space has 3 pivots. Okay, so this, and then this. So that's to show that the column space of A will only contain the matrices. Will contain the matrices, the columns, the first column, the second column has a pivot, and then the last column. So this will be the 3 vectors in the column space of A. So the column space of A is a 3-dimensional space, and so a vector space that is of 4 dimensions cannot be in the column space of A. So you can just say that no, U has 4 entries and cannot be a vector in the column space of A, which is of R3. That's 3 dimension. Okay, so that's enough to answer that question. All right, so let me try to bring up this a little bit. Okay, so I can still leave it that way. Let's just finish up the remaining questions here. So the VII says that we should the VII says we should determine if V is in the null space. Okay, we should determine if vector V is in the null space of A. Okay, so your V will be in the null space of A. Of course, there is a condition for that. That means if you can get AV equal to 0. Okay, so but then you can also use the approach we just used for VI now to answer your V. And what is to answer your VII? And what is that? Let's go up a little bit to see our V. Okay, so the vector that we were given as V, where is it? This is our U. Maybe we should come up a little bit. Okay, so here is our V, and you can see that our V has 3 entries. Okay, so while it has 4 entries. Okay, so when we performed the null space, we got that the dimension is T equal to 4. And of course, these were the elements of the null space. So by the time you perform this, you discover that we had T equal to 4. That's the dimension. And so our V now has 3 entries, and so it cannot be in the null space of A. Okay, so quickly you can just take note of that. So just you will go the other direction for this one now. This is VII. Okay, so of course your answer here will be no, and then you try to write your reason for saying no. And what is the reason? Our V has 4 entries. Sorry, 3 entries. V has 3 entries, while the null space of A, while null A is of 4 dimensions. Okay, 4 dimensions, sorry, is of 4 dimensions. So the elements of the null space of A has 4 entries each. So that means it is of R4, while our V has only 3 entries. Okay, and that's enough to answer that. So let us look at the next one, which is VII. Okay, I think that's the end of that board. Maybe we go to a new one. III, that's 8, says that we should okay, VII says that we should determine if V is in the column of A. Okay, so all right, now of course remember we said that V is not in the null space, that the column space is of 3 dimensions. Okay, and our V is of 3 dimensions. So clearly of course one, they have the same dimension. So we will now run the check. And what do we want to do? We want to check if we join V in the column space of A, are we going to get a consistent reduction? That means by the time we reduce it, is it going to give us a solution? Okay, so that means this implies that we want to check if we are going to get a solution by the time we solve this. That means if we get a value for vector x. All right, so let's try to do that quickly. So what is our A? Let's bring down our A here. So our A is 2, 4 minus 2 okay, yeah, 2, 4 minus 2, 1, and then minus 2 minus 5, 7, 3, and then 3, 7 minus 8, 6. So this was our A. But remember that after our matrix reduction, let me be sure. Okay, yeah. So but remember that after our reduction, we discovered that on the column space there were only 3 pivots, and the 3 pivots, okay, I think is in the previous page. Okay, let's go up a bit. Yeah, so we discovered that the pivots were in column 1, 2, and 4. So that means elements of column 1, 2, and 4 are going to be part of the column space. Okay, so in other words, our column space is going to be having only 2 minus 2, 3, then 4 minus 5, 7, then the fourth one, which is 1, 3, and 6. And then you will now join our V to it. And what is our V? Our V is 3 minus 1 and 3. Okay, so we will try to reduce this and see if we are going to get a value for the vector x. Okay, so let's try to do our reduction. So what's that going to give us? Okay, we will try to eliminate these 2, and in doing that our row 1 will remain the same. So we have 2, 4, 1, 3. So what's the algorithm? This will just be the addition of the 2 to eliminate. Okay, that will be 0. This plus this is minus 1. This plus that is 4, and then we have minus 2 here. And in this case, our new R3 is going to be R3 times 2 minus 3 times R1. Remember, we are using R1 to eliminate. Okay, so in doing that, 2 times this is 6 minus 3 times this, which is also 6. That will give us 0. Okay, then 2 times this is 14 minus 3 times this, which is 12. 14 minus 12 is 2. Then over to the next one, 2 times this is 12 minus 3, that is 9. Then lastly, 2 times this is 6 minus 9, because minus 3 times 3 is minus 9. So 6 minus 9 is minus 3. Okay, so that's the first reduction. So we go again. So in going again, we want to make this one 0, but okay, let's go ahead. I wanted to make this to be positive by multiplying through with minus 1, but that is not all that necessary. Okay, so here our root 1 and root 2 will be the same. So we have minus 1, 4, and 2. So in our row 3, we will try to eliminate 2 here. And what will be the algorithm? Just use R3. Of course, to make this to be of equal value, you multiply by 2, but their signs are opposite, so you just add. So 2 times R2. Okay, so of course 2 times this is minus 2. If you add the 2, you will get 0. Then here you have 9. 2 times this is 8. So if you add, you will get 17. Okay, and finally here you have minus 3. 2 times this is 4. And when you multiply, when you add, you will get 1. Okay, so and then that is done. So what do you have there? So you just have that. So you can see that in fact this is not just consistent alone. It is going to give you a particular solution because all of them have pivots. All right, sorry, all the 3 entries from the column space have pivots. So this is going to be very much consistent, because if you add our x now, remember that there is a separation here, so you are going to get something like, from the last row you will get 17x3 is equal to 1, which will give you that x3 is equal to 1 over 17. So it's going to be consistent. All of the x values will get a value. Okay, so if you put x2 as here you have minus x2, then plus 4x3 equal to 2. If you solve here, you get a value for x. Then if you put this one as 2x1, 4x2, x3, and all of that. So, but you don't need to solve this. That's actually what I'm trying to show, which is the reason why I'm not solving it. So all you need to do is to, of course, at the end of this row reduction, is clear that this particular system that we started with has a solution. So you just conclude that since ax equal to v is consistent, therefore we have an x, a vector x, that is going to make this to be true. So we can conclude, since this is consistent, therefore our v is in the column space of A. All right, and that is a good conclusion. All right, so I think that is for VII, which is 8. So we then go to IX, which happens to be the last question on that module 4 2B. Okay, and what is that? They said we should find the rank of A. Okay, so, and they gave us a hint there that the rank of A, in fact, even without reading the hint, the rank of A is simply equal to the dimension of the column space of A. The dimension of col A. Okay, so if you can get the column space of A, the dimension is simply the dimension of that col space is simply equal to the rank of your A. And we've already said here, like what we even used here, remember that it is the dimension that gave us these three vectors that formed column A. All right, and it has 3 vectors. So that's the 3 pivots we got when we reduced the whole A into echelon form. So it's easy to now note that the rank of our A is equal to 3. So you don't necessarily have to reduce it again. That's actually what I am saying. So you just have your solution that the rank of our A is equal to 3. Okay, so we are done with question 2. So we now go over to question 3, which is the last question for module 4. Okay, so for question 3, the first question A there says that fill in the spaces involved. Okay, so it now says if a matrix A is an n is A is an M by N matrix. Okay, so they are now asking the following question. So let me bring this down. So the first question they asked is, then a typical vector V is in null A if what happens. Okay, let me read that. Then a typical vector V in null space A has the property that AV is equal to 0, while a typical vector V in column space of A has the property that AX should be equal to V, should be consistent. That's exactly what we just did up there. That's what they're asking us here. So they are saying that if this is that, then a vector V will be in the null space of A if A V is equal to 0. This one is given. Then they are now asking what will now make so V will now be in the column space happens. That's exactly what that question is saying. If what happens, okay, and we did that up there. We said that V will be in column space of A if this guy is consistent. So if you solve this and you have values for X, then you know that your V is in the column space of A. So to fill in here, you will just write that this will hold if AX equal to that V is consistent. Of course, you should be conversant with the meaning of consistency of a particular equation. Okay, equation of linear system of linear equations. So for a system to be consistent, it means that the values for your x1, x2 up to xn, that they exist. Okay, so and that's the answer for that A. We go over to B. So sorry, this is actually AI, so we are dealing with AII now. Okay, so AII, they said there that if the null space of A is the zero vector, the null space of A is the zero vector if and only if, remember I'm using that abbreviation, if and only if AX is equal to 0, has only the trivial solution, and you know the trivial solution is where all your X values are equal to 0. Okay, so it now says, the question is now asking us, while column A, that's the col space of A, will be equal to a vector space R of dimension M if and only if what happens. Okay, so if and only if AX equal to B behaves in what manner? That's what the question is saying. So they are giving you a definition, and they are using that definition to now ask you a corroborative question. So the question here, or the information here, is that the null space of A being equal to the 0 is equal to the 0 vector will happen if and only if AX equal to 0 has only the trivial solution. So column space of A will be equal to a vector space of dimension M if and only if this is equal to B, implies that your B, first of all, this has to be consistent. I'm writing what you will fill in now. So this particular, let me use this guy. So that's the space you're filling. So AX equal to B must first be consistent. Okay, so if it is consistent, then the next thing is that your AX equal to B is consistent, and B, okay, or let me put it this way, is consistent for all, okay, let's do it that way, is consistent for all B in Rm. Okay, so that means it will be consistent for every vector B that you will pick from Rm. Remember that we did it when we said that vector V must be in col of A. We said that means that vector must be consistent if you solve it with the column space of A. If you add it to the elements or the matrix of the column space of A and then you solve, you should get a consistent system. That means there should be values for X. So now we are now saying that remember we said the first thing we determined in that V is that we showed that the V has the same dimension as the elements of column space of A. So here we saw that V has 3 entries and all the elements of the column space of A had 3 entries also. So we are now saying that for this to be in the column space, for the column space of A to be equal to Rm, all elements of Rm must have the same dimension with the column space of A, and then if you put them in this equation, they should all be consistent. All right. So and that's that for question A. So we go over to B. All right. So for B, we are told that there are two matrices, matrix A. So let me write down matrix A now. So matrix A, we are given and for matrix B, we are given that B is equal to, okay, so let's write out our B. Oh, sorry. This A actually has 4 rows. Which one did I omit? Okay. 1 minus 2 minus 4, 3 minus 2. Okay, I omitted the 3rd row. The writing was mixed up. Okay. So here we have minus 7, 8, 10, 3 minus 10. So this one is now the one I removed, which is 4 minus 5 minus 7, 0 and 4. Okay, so here this one is actually 4 entries also. So here we have 1 minus 2 minus 4, the same first row, 8. Actually, this one is a row reduction of the first. You are going to see that 0, 0, 0. Then this one is 3, 0, 0. Then 9 minus 12, 12. Then every other place is 0. Okay, so every other place there is 0. Okay, so and okay, no. Okay, so and the question now says that it says that matrix A and B are row equivalent. That means it was this matrix that was reduced to get this. That's actually the row equivalence there, and that's why I told you that both of them are the same. Okay, and that's the information that told us that. Okay, so they now said find the following. So they're asking us to find the dimension of null space A. So the null space of A. Okay, so recall that from what we did in question 2, the null space the dimension of the null space is simply equal to the dimension of the original space, the original matrix. Like here you can see, you can use the columns actually. So you can see it has 5 columns, and then the dimension of the null space will be the free variables that you have left. So, and what are the free variables in this place? First of all, to get the free variables, you need to get the pivots. So there is one pivot here, and there's another pivot. That's the column pivots. Of course, it's only columns that have pivots. So there are 2 pivots here. In other words, okay, sorry, the second one I circled is not a pivot. So there are only 2 pivots here. That means we have 3 free variables, and you can see x1 and x2 are pivots. So x3, x4, x5, whatever, will all be are all going to be free variables. So in other words, to get our dimension for the null space, you would take the number of columns, which is 5, minus the pivots, okay, and that will give you the free variables, which is equal to the dimension you're looking for. All right, and that's for I. We go over to II. So II says we should find the dimension of the column space. So very simple. The dimension of the column space is the number of pivots. So this is just it, and you are done. Okay, number 3. It says we should find the basis for the column space. The column space of A and the row space of A. So we are looking for the basis. Anyway, we used plural here, so it would have been BSES. So but since I'm writing them differently now, it is IS. Okay, so basis of column A, or for column A, is what we are looking for here, while in the second one we are looking for the basis for row A. That's the row space of A. Okay, so and I'm going to just give you a small hint, and that hint is even mentioned in the solution. They said that the bases are the entries where you have pivots. Okay, so that will be the vectors that will be in the basis for the column space. So what do you mean? Of course, we've answered question on this before. So if you go up now, you will discover that we only have pivots on column 1 and 2. That means the basis for A will just be these vectors, the 2 vectors there. So if you just pick them and bring them down, that will be the basis of our column space. So let me use this kind of brackets. Okay, so that means the first element in our basis for column A will be 2, 1, then minus 7 and 4. Okay, comma, then the second element will be minus 1, then minus 2, then 8 and minus 5. Remember, you will pick the elements of the basis of the column space from the original matrix. What the reduced matrix will do for you is just to show you the entries to pick. So the pivots here will tell you that you will pick the column 1 and column 2. If column 4 had or column 5 had a pivot, then you also pick the column 5 of the original matrix. But when it comes to the basis for the row space, you are not picking the original matrix. You are picking from the reduced matrix. And what are you picking? You are picking the non-zero rows. The non-zero rows. Okay, so that means I'm going to, oh no, I shouldn't clean that. Instead of cleaning it, I will cut it out. Okay, let me, oh no. Okay, let me drag this down. Okay, all right, so I can now remove this and then bring it down myself. Okay, so the basis for our row space of A will now be the entries on the that are non-zero. What that means, row 1 and row 2. Okay, so let's go there. So our row 1 is 1 minus 2 minus 4, and then what else? We have 3 and minus 2. Okay, and then the second entry there, which is the second row, is equal to 0, 3, 9, I think minus 12. Yeah, minus 12, 12. Okay, so and then you close. Okay, so here you can clearly see that both of them have the same dimension. All right, so let's now go, but that's not what you are asked. You are just asked to produce the basis for the both of them. And then the final question here is IV. It says we should find the rank of A. So the rank of A, remember we said that the rank of A is equal to the dimension of the column space. And since the column space has dimension 2, therefore our rank is equal to 2 also. Okay, right? So, and I think that is the end of question 3, right? So meanwhile, there is a question 4, which we are going to look at. I thought that question 3 is the last question in this module. I didn't know there was a question 4. Oh, this exercise is beautiful and plenty. Okay, so there is a question 4. So let's quickly look at that. All right. Let me increase this a bit again. So for question 4, it starts by saying that we should find, let me read here. The question 4 says that we should find the basis and dimension of set H, where H is given as this. Maybe I should write this. Find the basis and dimension of the set H. Of the set H, where H is equal to the set of A, B, C. That means it's made up of vectors of 3 entries such that A minus 5B plus C, 9C plus 9C is equal to 0. That's 1. And then 2 minus A plus 3B, plus 4B, not 3. Then minus 3C is equal to 0. What else? That's not all. There's another one, which is 2A minus 8B plus 4C, not 4, 9C is equal to 0. Okay, so okay, so this is the set H, and they say we should find the basis and dimension for that H. So how do you go about that? So let's see. Okay, so what do you do? First, the hint there says we should consider the solution of AX equal to 0. Okay, of course, for you to begin to look for dimension and basis, you will need to consider the null space. Okay, so we are going to be looking at the null space. So we will first of all get our AX equal to 0. And to get our AX equal to 0, that means we need to extract matrix A, and then our X will be your ABC, and then we equate to 0, and then reduce it to echelon form. Okay, so let's try to do that, and that's going to give us our A is simply the coefficients of this in our row form. So you are going to have your A, the coefficient of A in the first one is 1, then minus 5 is the coefficient of B, and then 9. Actually, the two ways you can see it, is to pick out the coefficient of A, B, and C, put in a row form, or pick out the coefficients of A in the three of them and put in a column form. That's just it. So the coefficient of this is -1, then 4, then -3. And then here you have 2, -8, and 9. Okay, so this is your matrix A. And then your X is your A, B, C. Alright, the beautiful thing is that if you open up this bracket again, you will get back all these equations. And then on the right side, you have 0, 0, 0, which is the 0 vector here. Okay, so we will now try to reduce this vector into echelon form. So we will, in this case, you don't have to bring in the 0 to form an augmented matrix, because the 0 is 0, so it won't make any difference. So let's just bring down our matrix the way it is and then try to reduce it. So in reducing this, we are going to have our row 1 will remain the same. So we are only going to reduce row 2 and 3. And we can see for row 2, they are equal in value, just opposite signs. So you add. So if you add this and this, you get 0. Add this and this, you get -1. Add this and this, you get 6. Here, what do? Make this, remember that this is the pivot you're using. Make it to be equal to this by multiplying with 2. So you have row 2 times, and then row 1 will be row 2, you bring it down, row 1 will be multiplied by 2. And since the signs are the same, you subtract. Remember, we've been doing all of this. So I'm going to have 2 minus 2 times this, which is 2 minus 2, 0. This is -8 minus 2 times this. Minus 2 times this will be 10. So plus 10. And so here will give us 2. And then here you have, oh, why did I remove that? Okay, I need it. So here you have 9. Minus 2 times this will be -18. And 9 minus 18 is -9. All right, so we'll now try to reduce this further. And to reduce this, we are going to eliminate this other 2. So in this case, our -1 becomes a pivot. So that means our row 1 and row 2 will be the same. So you have -1, 6. Okay, so in reducing this, of course, here will still be 0. What will be our algorithm? We are replacing R3, and R3 is 2. To make this to have the same value, you multiply by 2, but since the signs are opposite, you add. So this is going to give us 0 here. Now for this case, you have -9 plus 2 times 6 is 12, so you get 3 here. Beautiful. So you can clearly see that that all the rows or all the columns have pivots, okay, and that's very beautiful. So that means the basis is exactly the whole column vectors, while the dimension is equal to 3. Okay, so nothing serious here. Oh, sorry. Okay, sorry about that break. All right, so what sorry, I said the basis is the all of that. No, remember that the bases are formed from the free variables. Sorry about that. The bases are formed from the free variables. Okay, and there are no free variables. All of these are all pivots. Meanwhile, come back to this question up here. I think that's question 3. Okay. Permit me to go back to question 3 to confirm something. Okay. Okay, so all right, okay, it's all right. Okay, So let's come back here now. So you can see that clearly for this one, there are no free variables, and so since there are no free variables, that means our basis and our dimension of h are all zeros, because you can clearly see that all the columns here, they have pivots, so there are no free variables. And so but then you can see that you can actually see that the dimension of the column space is equal to 3. Remember that the dimension of the column space is different from the dimension of the whole space. Okay, so the null space, sorry. And it is the dimension of the null space that gives us the dimension of the particular matrix that you are given. So, but in this case, the dimension of the column space is the number of pivots you have, and the number of pivots is 3. Sorry, I was mixing up that with the previous question. Okay, so this one, the dimension of the column space is 3, but then that also tells you that the dimension of the null space is 0, because the dimension of null space is always the number of columns, in this case is 3, minus the dimension of the column space, which is the number of pivots. So 3 minus 3 will actually give you 0. So that means this particular matrix has no basis and no dimension. Okay, so just go ahead and say that no basis, and then if there is no basis, then the dimension will be 0. So you have no basis and then 0 dimension. Okay, and that is the solution to that problem, which happens to be the last question in module 4. Okay, and so we'll end for this section at this point, which is for module 4, so that we will know that module 5 would start on an entirely new section. Okay, so this is where we end it for this video. Kindly subscribe to the channel, give a thumbs up, and then make comments so we know that you're following. We'll see you in the next section. Bye.